Hello, and welcome to the lecture on BMS temperature measurement, and thank you for joining me in the transition to sustainable energy. In this lecture, we'll discuss temperature measurement in lithium-ion batteries. We'll discuss the goals of temperature measurement, which helps us ensure appropriate parameters for our sensors and for the related controls. Sensor placement, that is how many sensors we need and where to put them. The difference between thermistors and thermocouples. A thermistor circuit and thermistor equations. Let's start with why we measure temperature and how we use that measurement. Okay, why might we measure temperature in a battery? I'll tell you 2 reasons to do it and 1 reason not to do it. Please make your own list before you hear me out. System controls may require information about battery temperature. For example, lithium-ion batteries generally should not be charged at temperatures below freezing. To avoid charging when the battery is below 0 degrees centigrade, the system must have a temperature measurement. Also, when the battery is near its max operating temperature, the system should decrease current to avoid additional self-heating. If for some reason the battery gets too hot, especially a battery prone to exothermic behavior, we may wish to detect the event so we can issue a user alert or to trigger automated mitigation, if such exists. Some battery systems omit temperature sensing. For example, small systems such as remote control airplanes and drones. Inexpensive, minimal battery systems may have a very minimal battery management system, perhaps implementing only under-voltage detection. If there's no processor to calculate current limits and no actuator to enforce current limits, there's nothing to use the temperature measurement. A small enough battery may not pose enough risk for users to want to pay for safety mitigations. Let's consider 3 example systems and discuss whether they warrant cell temperature sensing. Electric cars typically do incorporate battery temperature sensing. The vehicle communicates with the charger and controls its motor, and so can implement current limits at cold and hot temperatures. And vehicle batteries tend to have heating and cooling systems. Vehicles have relevant actuators that require temperature information. Regarding safety, the large size of the battery carries significant consequences should something go awry. And the cost of temperature sensing is small relative to the total system cost. A home energy storage system is similar to a car. Quite possibly, the safety case is even more important, since a car typically has an awake and aware driver who can notice and respond to a safety event, while a home's occupants may be disabled or young or asleep or otherwise unable to notice and respond to a safety event. A small drone, on the other hand, probably does not warrant a battery temperature sensor. Batteries are typically removed from a drone for charging, so the drone could not limit the charge rate of a cold battery, and the discharge rate controls are often relatively rudimentary. The small size of the battery means any safety events would be correspondingly small. And in this inexpensive product where weight is critical, many users would balk at the added cost and weight of temperature sensors. Unlike cell voltage sensing, battery temperature sensing may be omitted in some systems. Let's move on to sensor placement. How many temperature sensors do we need? Do we need a temperature sensor on every cell? For controls, it turns out that we can do pretty well if we sense a few locations and use a model to estimate the temperatures in between. In the design phase, some batteries would be thermally characterized. That is, lots of sensors would be installed and the battery would be charged and discharged at different rates and at different ambient temperatures. The resulting data would be used to build a thermal model of the battery. In the product, we would use this model along with real-time sensor data to estimate temperature between the sensors. How many sensors we need comes down to the quality of our model, how much variation we expect from one unit to the next, and how much residual error the system can tolerate. Now, let's consider the perspective of safety. We want to prevent actions that lead to overheating to prevent immediate failure. For example, if the battery is already quite warm, we want to reduce the allowed current to limit further self-heating. This is really a controlled scenario, with sensor placement assessed as in the previous slide. We also want to protect the battery against use in ways that might cause internal damage and increase susceptibility to future failure. This is, again, a control scenario. What about exothermic behavior? What if, in spite of good design and good manufacturing, we have a severe fault, perhaps due to some external accident causing a battery fire? If we sense temperature on one cell, while the fault originates at another, there will be a delay before we detect the fault, and temperature changes are slow, so the time delay may be relatively long. So, we might need a sensor on every cell to detect high, rapid overtemperature quickly. But do we want to? When the battery is on fire or exothermic, the BMS can't do much. Typically, a BMS can implement controls to prevent some pathways to this sort of failure, but it is helpless if the failure is already in progress. And lastly, catastrophic failure typically shows up in the cell voltage, which the BMS is already monitoring for every cell. Here is a plot from a publication where the authors caused thermal runaway by rapidly heating the cell until the cell itself began rapidly self-heating. Time is on the x-axis. The pink line is temperature, which rises steeply as expected of exothermic behavior. Concurrently, the cell voltage plummets, and in a product, this would trigger an under-voltage flag. In practice, most vehicle battery designs that I've seen incorporate a few temperature sensors. For example, the Chevy Bolt has 6 sensors, and the Nissan Leaf has 4, as Professor Weber shows in his thorough battery teardowns. In summary, a sensor on every cell could detect thermal runaway events, but so can the voltage sensors which are already present, so typically this is not done. A few sensors for the whole battery pack suffice for controlling battery pack cooling and heating and for setting the max allowed current. Thus, this is the typical solution in practice. With that, we might go back to this slide from earlier and modify it, moving the detection of thermal runaway out of the purview of the thermal sensor. Let's talk about what sensor to use to measure temperature. Every battery design that I've seen uses thermistors, but I've heard some young engineers mention thermocouples, possibly because they've heard of them in the context of lab instrumentation. So let's compare the two. A thermistor is a thermally sensitive resistor. As temperature changes, its resistance changes. A thermocouple consists of 2 dissimilar metals bonded together, which generate a variable voltage as temperature changes. Thermistors have a narrow temperature range, but still well beyond the operating temperature range of a battery. Thermocouples drift more over time, which means for good accuracy, they require periodic calibration. Thermistors are more accurate. Both sensors have a similar response time, and thermistors are much less expensive. Consider which of these parameters matter for battery management. The low drift and better accuracy of thermistors is a nice feature. In-field calibration can be tricky to implement. But really, the cost is what makes thermistors much more appealing for a product, especially when we want to place several of them. Finally, let's take a look at some implementation details. Here's a typical thermistor circuit, a resistive divider consisting of a resistor and a negative temperature coefficient thermistor. We apply a stable reference voltage and measure the midpoint voltage Vtemp, which is equal to the reference voltage scaled by the ratio of the resistances. As the NTC thermistor resistance changes, so does Vtemp. As temperature goes up, the NTC resistance goes down, and since the numerator on the right decreases, the output voltage on the left of the equation also decreases. If we plot Vtemp, it looks like this. We see a nice measurable slope for the range of temperatures that matter for lithium-ion batteries. It turns out that the resistance of an NTC thermistor is not linear with temperature. Many manufacturers provide measured data, which I've plotted here, and also plotted with a logarithmic scale on the y-axis. The data is well fit by an exponential equation, and thermistors are often described by the parameters of this equation. The correspondence between the data in green and the equation in pink is not perfect, but it's pretty good, especially for the temperature range where a BMS most cares about accuracy. In practice, you would take these two equations and also the specified tolerances for your thermistor and voltage sensor and create a big spreadsheet to calculate your worst-case total temperature measurement error. You'd go back to the thermal model and derive from it requirements for temperature measurement accuracy to get good controls. And then, check whether the design meets the requirements. This is likely an iterative process. Even if your first design meets the requirements, you might try a less expensive thermistor with looser specs until you meet the requirements at lowest cost. Optimized temperature sensing requires multidisciplinary collaboration. Cell engineers define the battery temperature requirements. Thermal or mechanical engineers characterize the battery pack's temperature under different operating conditions. Systems or controls engineers develop a controls model from which accuracy requirements can be derived. And electrical engineers design the temperature sensing electronics to meet the necessary requirements at minimum cost. And that's how we get to an optimized design. This concludes the lecture on battery temperature measurement in my Battery Management Systems course. If you liked what you saw and would like to see more, please let me know.